All right, everybody, what is going on? Today we're going to be solving another LeetCode problem. This one is called valid Sudoku. It's a medium, and we're going to be answering it in C++. So let's get into the problem. So basically, we're given a 9x9 Sudoku board, and we need to return true or false depending on whether or not it abides by the rules of Sudoku. And those rules are each row must contain the digits 1 through 9 without repetition. So basically, in each row of the board, there cannot be any repeated digits. Every cell can either be empty or it can be a digit 1 through 9, but we cannot have any repeated digits. And the same applies for the columns, and the same applies for the boxes. So we have these 3x3 boxes where the rule also applies. So basically, I'm just going to get into the solution here. So the way we're going to do this is I'm going to have 3 9x9 vectors where we're going to keep track of the numbers we have seen in each group of columns, each group of rows, and each group of boxes. Now there's going to be 9 groups of each because, as you can imagine, there's 9 rows, 9 columns, and also 9 boxes. So, and I'm going to store all of these as booleans. It's going to be false if we have not seen the number, and then true if we have seen a given number in that group. So bool, we'll say bool calls 9, and we want this first dimension to be 9 because there are 9 different columns. And then we need the next dimension to be 9 because there are 9 different possible numbers that we could see in each of those 9 columns. So we'll initialize all of these to false, as in we have not seen them. And we need to do the same for the rows and the same for the boxes. Now, you might be wondering, so columns, easy enough, because for columns you do 0, 1, 2, 3, etc. That's how you mark them. Same for the rows. 0, 1, 2, 3. But for the boxes, it's like how do you map, I and j to the boxes? Well, there's a formula for that, and once we get to that part of the problem, I'll explain it. So basically, we just want to iterate through the board. So, and we know the board is constant size, like I discussed. Maybe I didn't discuss that in this take, but we'll talk about it more. So, but we know the board is constant size, so we can just hard code a 9 in here. And then we need the inner for loop for the rows. And then basically the first thing we want to do is, notably, the numbers are stored as strings, or actually characters, rather. They're surrounded by quotations here, so it's a bit misleading, but they're characters. So we're going to have to convert the characters to integers. That way we can utilize these indices here. But before we do that, the first thing we can do is just check if there is even a number there in the first place. Because if there's a period here, then we can just skip. So we can do a simple if statement to check that. So if the position of the board, or if the element at the position ij on the board is equal to period, then we can go ahead and continue, just skip that cell, because there's nothing there. Otherwise, we got to do stuff. So the first thing we can do, obviously we've got to populate these data structures to mark numbers that have already been used. But before that, we can check if the number has been used. So we'll say if calls at I, and then the num. Well, first, how do we get the num? We got to write some code for that. So the number, because we got to convert it from a we've got to convert the current cell we're at from a character to an integer. So that we can do that by saying board at ij minus the character literal 0. And basically the way that works is, like, imagine you have 0 here, that'll normalize to 0, or if you have 1 there, that'll normalize to, or convert to the integer value of 1, etc., etc. So, but now that I think about it, we don't start from 0. We start from 1, right? We go from 1 through 9, but we need a 0 indexed value. So to account for that, we just have to subtract by 1. But then that'll give us the desired number to use in these data structures. So if calls at I is true, then we need to return false. But there's 2 other cases where we return false also for rows, j for that num, and then also for boxes at box index, which I was discussing before. We need a way to map the box index to the corresponding box, and I'll show that now. So for a given num. But anyways, if any of those are true, we know we can return false because we have a repeated number, and it's an invalid. Thus, it's an invalid Sudoku board. But to get the box index, we're going to use this formula. So it's going to be I divided by 3 times 3, and I'll use lots of parentheses here to make this very clear what's happening, and then we add that to j divided by 3. And then basically what this does is it's going to take the cell at position ij and then map it to a box index between 0 and 8. And the way that works is, let's just do a few examples. So I'm going to label each of the boxes like so. 6, 7, 8. Now basically 0 is going to correspond to the index that we're going to use to represent this top left box. Likewise for all the rest of the boxes, and then, you know, all the way to 8 is going to represent the index for the box down here. And this formula will map the cell number to these box indices. So say, for example, you're at, let's just take a random cell here. So say you're at I equals, let's see, 0, 1, 2, 3, 4, 5, 6, 7. Well, this actually be j, but j equals 7, and then we'll just say I equals 0, 1, 2, 3. So we'll say I equals 3, j equals 7. Now it's like, what box does that map to? Well, if it's this cell, obviously that should map to box 5 here, right? So let's plug that into our formula. So our box index is going to be equal to this formula, and let's plug in those numbers. So we have I as 3, and we have j as 7. So this is going to be and remember, integer division, any number, so if you had 1 divided by 3, that would go compute to 0. Likewise, basically your you know, if you have a fraction that's below 1, that'll compute to 0. Otherwise, any decimal places are just going to get truncated off, and it's always going to result in an integer value. So nevertheless, 3 divided by 3, that's going to be 1. So 1 times 3, and then plus 7 divided by 3 is going to be what, 2 and 1/3, but the 1/3 is going to go away, so it's just going to be 2, because it's good, the decimal is going to get truncated. So you have, for your answer, you're going to have let's see, 5, right? And that checks out. It's box number 5. So that's basically how that algorithm works. You can try it for any cell coordinates. But now that we have the box index mapped out, we can safely check this, and then also we can use that to actually flag, like, So if we don't find a repeated number and we're not returning false, we need to flag the current number as being used in each of these data structures. So that code is basically going to look like this. We use the same we're accessing the same elements here. So columns I, num, we're just setting that to true because we have seen it there. Likewise for that one, and then same for the boxes. And this is pretty much it for the algorithm. So after that, we can just return true because we know if we made it all through every cell without any repeated values, we know it's a valid Sudoku board. So go ahead and return true there and just see if there are any noticeable bugs here. I'm just gonna go ahead and run this. So accepted the initial test cases. Now if we submit this, we can look at our percentages. So beats 98% in terms of runtime, and then also memory is good. It beats 85% because we're just using Boolean arrays here, so it's pretty compact. Now the time complexity for this is, now if the board were to scale, you would have like a time complexity of n squared, where n is the length of the side of the board, you know, assuming the board is like a square. But it says in the problem statement that the board length of both sides is always going to be 9. So with that being said, I would argue that the time complexity is going to be constant, because regardless of the test case that's thrown at you, according to this specific problem, the board is always going to have the same dimensions. So if you think about that, you're always going to be having 81 steps every time this algorithm runs. So this is going to be constant time. Now, again, this is a little bit controversial, I've noticed, for this problem, because it's like, if the board scales, like, of course, you know, your time complexity is going to change, but it's very, you know, clear in this problem that the board size does not change. So I would argue strongly that this is constant time. And with that being said, it's also going to be constant space. So I hope you guys enjoyed this video, and if this helps you at all in your understanding of this problem, please leave a thumbs up and subscribe if you want me to make more. Helps me a lot. And yeah, see you guys in the next one.